nervous system has two types of cells, glial cells and neural cells. Here we have a neural cell, known as a neuron. At the top end, we have dendrites, which is where impulses are received. Then we have the nucleus, and as you go on, we have the axon hillock. This is where it becomes a little thinner and becomes the axon. Then at the other end, you have the axon terminals. This is where the presynaptic junction is, and where little neurotransmitters, presynaptic neurotransmitters, are located to perform other junctions with other cells. Also, not all, but certain neurons have something called a myelin sheath. This is a structure that kind of looks like this on a neuron, and what it does is it helps in neural transport, like impulse transport, and kind of acts as a conduction factor. It really helps in the speed of conduction impulse.
This is the resting membrane potential. It is due to 4 different things. 1, the inequality of the ions, which means that inside the cell and outside the cell is different. That's why it's called a potential, because it has the capacity to change. So outside of the cell is going to be more positive, and the inside of the cell is more negative. It's selective permeability. So that means that everything can't just go wherever it wants. It has a certain system where certain products are going to be inside, and some things will be outside. Things that help regulate it are the sodium-potassium pump, because as we'll show you later, there's different amounts of each one inside the cell. So inside the cell is more potassium, outside the cell is more sodium. And then anions, which are negatively charged ions, are inside the cell, which is why the cell is normally negative 80 millivolts to negative 60 millivolts. And a way to remember what is on the inside and what is on the outside is, hey, sodium, do you want to go to the movies? And sodium says, nah, because it's antisocial, so it doesn't go. And potassium says, K, so potassium is just inside by itself at the movie. Resting membrane potential.
Okay, so now we're going to talk about IPSPs and EPSPs. So these occur when one axon is communicating with another axon when you're trying to transmit an energy signal from one to the other. So here would be your presynaptic terminal. That's going to be your axon terminals that Val talked about at the end of the axon. And then this is going to be your postsynaptic terminal. So this could be, it could be like making contact with the soma. It could be making contact with the dendrites or anything like that. So Janessie is going to talk about excitatory postsynaptic.
So EPSP is excitatory postsynaptic potential, and basically it moves the cell closer to threshold by allowing the positive ions to come in through the sodium ion channels. And an example of that would be glutamate.
Then you also have your IPSPs. So IPSPs are inhibitory postsynaptic potentials, and what those do is they're going to make the cell become more negative, causing it to move away from threshold and less likely to fire. So those are an example of that is going to be your GABA.
So you have 2 different ways that electrical impulses are propagated through the neuron, and one's going to be passive and the other is going to be active. So first talk about the passive. So that's also known as the local potential. So that's going to be different with amplitude, and it can either depolarize or hyperpolarize the neuron. So it's going to be located here around the axon hillock. It's pretty small in distance just because it's passive movement. It's not involving ATP, so it's not going to be able to travel as far as the action potential is. A couple other things, it has different ion channels in which it communicates with other nerve cells, and it's going to include modality nerve cells and modality gated channels and ligand gated channels, which respond to different pressure, different chemicals, and stuff like that. So the amplitude can vary in terms of how many chemicals have been received or how much pressure has been put on a certain cell, and then from there the amplitude is going to be small or it's going to be big, and then it's going to generate a certain amount of energy. and then from there it will build up and it will affect the action potential, which Alyssa is going to talk about.
So action potential is going to be a little bit different. Instead of being located here, it's going to travel the entire length of the axon. And it can do that two ways. First would be an unmyelinated way, which is a slower conduction. So the myelin helps speed up the things. So if it's unmyelinated, it's going to be slow and it's going to go the whole direction. But if you have myelinated, so that'll be with your myelin sheath, you're going to have a faster conduction, and the name of that conduction is a saltatory conduction. And the reason it's going to be faster is because you're going to have a skipping motion over your nodes of reindeer. So it's going to be a faster conduction when you have myelination.
Action potentials work in a cyclic fashion. The cycle starts with the resting period, followed by the threshold phase, depolarization, repolarization, and the hyperpolarization phase, which is split into the absolute and relative refractory periods. Once the relative refractory period is completed, we arrive back at the resting period to begin a new cycle. To complete an action potential generation cycle, multiple changes in membrane potential need to occur. During the resting period, without outside stimulus, the membrane potential falls at about -70 millivolts. When a large enough electrical stimulus is received, the membrane potential becomes less negative to about -55 millivolts. This is the threshold phase. During the depolarization phase, the membrane potential increases rapidly to about +30 millivolts, followed by a rapid decrease during repolarization. Hyperpolarization occurs when the membrane potential becomes more negative than its initial resting state. Once the nerve returns to its resting membrane potential, the cycle is ready to start again.
Okay, so reviewing what Amanda said earlier, we're going to talk about the resting period of a cell, which is where your cell's at when it hasn't received any stimulus whatsoever. It's at -70 millivolts. The inside of the cell is going to have a higher concentration of anions and potassium, and the outside of the cell is going to have a higher concentration of sodium and chloride. After a stimulus is received, you have the potential to have an action potential. If it reaches -55 millivolts, which is a less negative charge than the -70 that you had before, you're going to reach threshold and you will fire an action potential. That's where the all or none principle comes in. If you don't reach the -55, then you're not going to have an action potential.
Okay, so the next step after the threshold has been reached is depolarization, and the membrane potential is going to pop up to a maximum of 30 millivolts. And this is done by changing the ion concentrations inside and outside the cell. So the sodium channel opens and sodium flows from outside the cell to inside the cell to bring up the intracellular charge to be more positive than outside the cell. Once the maximum of 30 millivolts has been reached, you then enter repolarization, in which the sodium channels close and the potassium channels open. And they do this way the membrane potential can become more negative, meaning that the intracellular charge is going to become less than the extracellular charge. And they do this by having potassium flow from inside the cell to outside the cell, putting more positive charge outside the cell. We are now entering the hyperpolarization phase after repolarization, and it's broken down into two parts, absolute period and the relative refractory period. And during the absolute portion of hyperpolarization, no action potentials can occur. And this is because the membrane potential becomes more negative than resting. And that's because intracellularly the potassium is flowing out because the potassium channel is still open, making the intracellular more negative than extracellularly and more negative than it normally is. When we enter the relative refractory period, the membrane potential has hit its max negative point and is popping back up towards its resting potential. So action potentials can occur with an abnormally large stimulus. There is no change from intra to extracellular because the channels are closed,
but it is the membrane potential is returning towards its normal resting state because potassium, or the positively charged ions, are building up intracellularly.
Okay, I'm going to explain ionotropic receptors. So basically what they are, they're considered the fast receptors because all it is the receptor blocking the ion channel. So as soon as the neurotransmitter like GABA or ACH binds to the receptor, it's going to open up the channel. So basically the neurotransmitter binds to the receptor, it goes away, and then the ions like sodium and chloride are able to flow into the cell. It's really important for our neuromuscular junction because when ACH does bind to the when ACH binds onto the receptor, it's going to stimulate the release of calcium in the sarcoplastic reticulum.
Okay, I'm going to talk about metabotropic receptors, and they're going to, like, the ions will connect to it, and instead of going fast, it's going to be a slow reactor, so it has to first go to the G protein, and then the G protein will activate the enzyme to open up the gate for the ions to go in. So like dopamine or glutamate will synapse with them and get that process going, so it takes more time, but it tends to be more powerful.